Plants are in control of the process of getting these bacteria to come and then taking them in. And they'll feed these bacteria. In order to do this, they'll give them as much as 40% of the photosynthesis that they make.
Three things: amino acids, organic acids, and sugars are being released to control the microbiology in the soil.
Yes.
Interesting.
So as it turns out, most of these bacteria are, at least in the rhizophagy cycle, are staying just underneath the cell wall. The movement enables the plant to break these microbes up into smaller and smaller little protoplasts and replicate them. So the plant can replicate them. You had to be a botanical illustrator or fungal illustrator in order to show the features that you want to show. You can't take pictures of everything.
The key to taking up more nutrients is more root tips. In this video, we're going to get into it with James White and the rest of the team on Perfect Gardens TV. Please remember to like, share, and subscribe. And if you haven't checked us out on Instagram and Facebook, make sure to do so. And if you haven't seen that $2.99 membership with over 115 growers ready and willing to assist you through your growing practices, I highly recommend to check it out because you don't know what you're missing out on.
Make sure to hit the join button on the bottom of every video.
Okay, so the process, all of this rhizophagy cycle happens at root tips. And so you can see here, this is a grass. Grasses have a lot of root tips. You can see all the little lines all over these roots. Those are the tips of roots where rhizophagy cycle would be happening. So grasses do this a lot. And so they'd be getting a lot of nutrients from bacteria in soil through the rhizophagy cycle. But all plants do it. All plants do it in the roots, and they take it in, just some more than others. This is a grass root, and you can see the root tip here, and you can see the kind of a blue haze out there, the blue cloud around it. Those are the bacteria being cultivated in the zone of exudates, where the plant is cultivating those bacteria with exudates or sugars, right? So plants are smart. You know, this is one way that they're getting these back. They're controlling this process. Plants are in control of the process of getting these bacteria to come and then taking them in. And they'll feed these bacteria. In order to do this, they'll give them as much as 40% of the photosynthesis that they make, of the sugars they make. They're giving them to these microbes in order to get these other nutrients, these other soil nutrients from the microbes. So plants are in charge of this process. And to a plant, photosynthate is cheap, but these other nutrients are hard to get, the phosphorus and the potassium.
So the picture shown, would this be the process in where they're taking in and potentially ejecting, like or where they're actually coming out? Like, what part of the root is
this? This is the root tip here of a branch root. So you can see it coming out of this bigger root, right? And this is where they're taking them in. Further along in this root, once it gets bigger, they would be coming out on the root hairs, and I'll show you that. Okay. So you see what I'm talking about.
And not to be tomato, right? Are they sugars, or are they amino acids and peptides?
They are a mix of nutrients, mostly sugars.
Sucrose, glucose, those types of sugars, or are they
yes
evolved forms of sugars? Like they're
sugars that microbes might like.
They are actually sugars.
They are actually sugars, but they will also put out amino acids in certain circumstances, and also organic acids in other circumstances. They're essentially chemicals that the plant can control these microbes with. That's the important thing.
Three things: amino acids, organic acids, and sugars are being released to control the microbiology in the soil.
Yes.
Interesting. Okay.
Yes. Yeah. Plants are in control. Plants are ranching or farming microbes, soil microbes. It's a principle, right? So this is a root, and you can see the root cell. This is the epidermis. You see those little spears in there? Those are the bacteria. These are those protoplast stages. And you can see they're replicating in there. Okay, so the plant is actually replicating these protoplasts, bacterial protoplasts inside the cells. And let's see. Now this is one of my students, one of my graduate students, Celeste Song, and she actually did one of these tagging studies. And this is where she took a Pseudomonas and tagged it with a fluorescent stain called M. cherry, and then put it under the confocal microscope and examined it. And here you can see her scanning the image through these cells of what was this plant? I don't know, clover plants, I think. These are the root cap cells, and you can see the red things there. Those are the bacteria inside those cells, inside those plant cells.
Wow.
So yeah, no, you can see, and see that's labeled. That's labeled. So she knows the bacterium, Pseudomonas, and then she put this tag on it, and then she put it in, and now you can see it in the plant. You know, you can do this and see it in any parts of the plant. So we know where these microbes go because we can put a little label on them and then track them in the plant. So as it turns out, okay, most of these bacteria are, at least in the rhizophagy cycle, are staying just underneath the cell wall. Okay, so this is a drawing of that. This gray is the cell wall. And you can see the cell in the middle here. You see the little line that my arrow's going around. That's the plasma membrane of the root cell, right? And then you see the membrane. It's out there between that plasma membrane and the cell wall. So it's in this little space called the periplasmic space. So it's not actually in the membrane or in the cell itself. It just stays out there. And it's in that little space that the plant puts superoxide to dissolve the walls and make those bacteria leak nutrients. This whole thing, by the way, the plant, this is part of the plant control again. The plant is moving these bacteria around like this in a process we call cyclosis. So it's circulating like this around and around and around like this. And what that does is, okay, so the plant's hitting these microbes with superoxide, and then it's moving it. Those bacteria cannot, they're in total control. They're being constantly moved, and the plant won't let them reform their cell walls or produce enzymes or whatever it is. They can't. The plant is moving them. The movement enables the plant to break these microbes up into smaller and smaller little protoplasts and replicate them, so the plant can replicate them, but the microbes themselves can't then suddenly become pathogenic or something. They're under control in this process. So
the periplasmic area, this is kind of like, it's kind of like a waiting room and a conditioning room for the bacteria and what the plant was going to want to ultimately do with it.
Okay, not a waiting room, but a processing room.
Right. Conditioning
room is better.
Yeah.
Where these microbes are being processed right in there, and nutrients are being extracted. So
how long have we known that space was there?
So crazy.
Oh, we have known about that space for a long time, but we have not known that there are bacteria in that space. And the reason is because bacteria are not unless it's a disease, they're not supposed to be inside plant cells, right? Or animal cells, So we don't expect to see them there. So we don't interpret them as that. In fact, when people see them, they say, oh, there's some extracellular vesicles, right? Extracellular vesicles. Instead, they don't interpret them as bacteria or microbes, but instead some kind of extracellular vesicle or a vesicle outside the cell. So whatever they are, whatever that means. We have images of electron microscopy where they see these things, they show these things, and they interpret them as vesicles. So it's a phenomenon that you don't see something until you first see it.
What's with the variances in superoxides between those periplasmic spaces where some have 3, some have 1? Is that just the variances of what it's trying to extract from that bacteria?
No, that's just artistic rendition variation. Okay. We don't know how much they differ. Yeah. But when I made this diagram, I just had some of these 2 O minuses or O minus things. And then I just stuck them.
Got it.
No, that's cool.
Yeah,
that's cool.
That's what it is. So the enzyme on the
plant
cell,
you didn't go to school to paint the Mona Lisa, right?
Believe it or not, as a mycologist in the early days of mycology, I illustrated a lot of fungi, and yeah, I'm trained, believe it or not, as a botanical artist. Believe
Wow.
it or not.
That's
Believe
cool.
it or not.
That's
Yeah.
cool. That is
Yeah.
cool.
We all had to back in those days. We all had to. Now people don't do it, but back in the 70s, when I was in the early 80s, when I was training as a mycologist, we learned to do that.
It makes sense, right? You have to transcribe what you see in a book because the internet wasn't there. So how do you transfer your information to the rest of the world at their discovery?
And photography wasn't as good as it is now, too. We didn't have digital photography. Everything was light, like film photography. So everything was black and white. So you had to use that. And illustrations in botany, people illustrate things to show the points they want to show, right? So you had to be a botanical illustrator or fungal illustrator in order to show the features that you want to show. You can't take pictures of everything and show it because they don't show up good in pictures. Yeah, so you do have to be an artist. Yeah, good question.
Here's the Fit for 25B list. Essentially what this is list of active ingredients may be used in non-food use products under Section 4.8. It's basically the gobbledygook from the government. These lists, like see all these oils, these are considered environmentally safe. Doesn't mean they're human safe.